Our entire observable cosmos was once smaller than a single atom. In a fleeting moment, space itself stretched faster than light, sparking everything into existence. This is cosmic inflation, the rapid expansion that set the stage for every galaxy, star, and planet. By the end of this journey, you will understand how a quantum whisper created the entire cosmic web we see today. How could a universe so vast and smooth come from such an infinitesimal seed? What echo from that first instant might still be detectable today? What does it mean for our place in this grand narrative? A classic explosion is a chaotic event. Shrapnel flies in every direction, temperatures vary wildly, and the debris field is anything but smooth. If the Big Bang were merely that, a singular burst of matter and energy, then our universe today should reflect that primordial chaos. We should see vast deserts of cold, empty space bordering searing hot clusters of galaxies. The cosmic background radiation, the afterglow of creation itself, should be a patchwork quilt of wildly different temperatures. Yet when we point our most sensitive instruments at the sky, we see something profoundly different and profoundly puzzling. The entire observable cosmos, in every direction we look, is almost perfectly uniform. The temperature of that ancient light varies by less than 1 part in 100,000. It is a sea of stunning smoothness. This presents a fundamental problem, known to cosmologists as the horizon problem. Think of it this way: the universe is estimated to be around 13.8 billion years old. Light, the fastest thing there is, has therefore had 13.8 billion years to travel. Yet the cosmos we see is vastly larger than that. We can observe regions of space on opposite sides of the sky that are separated by over 90 billion light years. These regions have never been in causal contact. Their light has never had time to cross the gulf between them. They are like two strangers on opposite sides of a vast ocean who have never met, never exchanged a single word, and yet they are dressed in identical clothing, down to the last thread. According to the classic Big Bang model, there is no physical mechanism that could have coordinated this. How could these distant realms possibly have reached the same equilibrium temperature if they were never connected? It defies the basic rules of thermodynamics. Alongside this mystery of uniformity lies another, equally deep puzzle: the flatness problem. The shape of the universe is dictated by the delicate balance between the energy of expansion and the pull of gravity from all the matter and energy within it. If there is too much density, the universe is closed like the surface of a sphere and will eventually collapse back on itself in a big crunch. If there is too little density, it is open, curved like a saddle, and will expand forever into a cold, thin void. Our observations, however, point to a third, incredibly precise possibility. The universe appears to be exactly flat, balanced on a knife's edge between these two fates. The problem is that this balance is unstable. Any tiny deviation from perfect flatness in the early universe would have been magnified exponentially over time. For the universe to be as flat as we measure it today, its geometry at 1 second after the Big Bang must have been fine-tuned to an accuracy of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros, a number so incomprehensibly precise it seems to demand an explanation beyond mere chance. These were not minor quirks. The horizon problem and the flatness problem were gaping holes in our understanding, serious conundrums that suggested the story we were telling was incomplete. The classic Big Bang model described the universe's evolution beautifully from a hot, dense state onward, but it could not explain the initial conditions. It was like walking into a perfectly arranged room and having no idea how it became so orderly. The stage was set, the problems were clear, and the physics community needed a revolutionary idea, a mechanism that could rewrite that first fleeting instant and solve these puzzles in one elegant stroke. Into this landscape of cosmic puzzles stepped a young particle physicist named Guth. He was not a cosmologist by training, but in the late 1970s, he found himself wrestling with questions about the fundamental forces of nature in the universe's earliest moments. He was working on a problem involving magnetic monopoles, hypothetical particles left over from the grand unification of forces. The math was leading him to a strange and powerful conclusion about the energy of empty space itself. One night in December 1979, while reviewing his notes, the pieces suddenly clicked into place with a clarity that stunned him. He later described it as a spectacular realization. Guth saw that if the infant universe became trapped in a peculiar high-energy state, what physicists call a false vacuum, it would possess a bizarre property. This energy would generate a repulsive gravitational force. Instead of pulling things together, this form of gravity would push everything apart with incredible, relentless pressure. Space itself would be forced to expand, and not just expand, but to stretch at an exponential rate, doubling in size over and over again in fractions of a second. This was not an explosion of matter. This was space inflating like a balloon being blown up at a speed far surpassing light. In that breathtakingly short burst, a region smaller than a subatomic particle could be blown up to a size larger than our entire observable cosmos today. And with that single, elegant mechanism, the cosmological puzzles began to dissolve. The horizon problem vanished because the entire visible universe emerged from a tiny, causally connected speck that was stretched to cosmic proportions. Before inflation, that speck was small enough for heat to spread evenly throughout it, creating the uniform temperature we see imprinted everywhere. After inflation, that smoothness was simply magnified across the sky. The flatness problem was solved because inflation acted like a cosmic iron, stretching the fabric of space so enormously that any initial curvature was smoothed out to near perfection. Imagine taking a tiny, wrinkled crinkle from a piece of paper and stretching it to the size of a continent. From our local perspective, that vast surface would appear perfectly flat. Guth's notebook entry that night marked the birth of the inflationary universe theory. It was a conceptual leap of profound beauty, proposing an engine for creation's first moment that could set the stage for everything to follow. But a spectacular realization was only the beginning. For an idea to become a cornerstone of science, it needed to make predictions, to tell us what fingerprints this inflationary engine should have left behind for us to find. Guth's brilliant idea was a new beginning, but it demanded a physical engine. What kind of force could stretch the entire cosmos in less than a blink? The answer lies in a peculiar state of empty space called a false vacuum. Picture the very fabric of reality not as a flat, calm plane, but as a landscape of hills and valleys. The lowest valley represents the true, stable vacuum we experience today, a state of minimal energy. But in the universe's first sliver of existence, it may have become trapped on a high plateau, a false vacuum. This is not truly empty, it is seething with latent energy, a kind of cosmic tension frozen into the void itself. And this energy has a startling gravitational effect. According to Einstein's theory, gravity is not just about attraction. Energy and pressure warp space-time. The intense energy density of this false vacuum generates a powerful negative pressure, a sort of cosmic repulsion. Think of it like this: if you try to stretch a normal piece of rubber, it pulls back. But this false vacuum behaves like a bizarre, cosmic rubber that pushes outward the harder you stretch it. This repulsive gravity becomes the motor for inflation. As a tiny region of space begins to expand even a little, the repulsive force kicks in, driving it to expand further. That expansion creates more space, which contains more of this false vacuum energy, which drives even more expansion. It becomes a runaway, exponential process. Space does not just grow, it doubles in size and then doubles again and again, in intervals so brief they are measured in fractions of a trillionth of a trillionth of a second. In this fleeting epoch, a quantum fluctuation smaller than a proton could be inflated to a scale larger than our entire observable universe. But such a state is inherently unstable, like a ball balanced perfectly on the crest of a hill. Eventually, through a process akin to quantum tunneling, the false vacuum must decay. The ball rolls down into the true valley below. When this happens, the colossal energy stored in that false vacuum is released in a spectacular transformation. That pent-up tension is converted into a searing, uniform bath of particles and radiation, flooding the newly stretched space. This moment, the decay of the false vacuum, is what we traditionally call the Big Bang. It was not the beginning of space and time, but the fiery beginning of matter, light, and the universe as we describe it in classical cosmology. Inflation set the stage, creating a vast, smooth, and flat expanse, and then handed it off, fully primed, to the familiar hot expansion we have been studying for decades. The engine had done its work, but it would have left behind unmistakable clues in the structure of the cosmos itself. The sheer magnitude of this event defies every human sense of scale. To say the universe expanded rapidly is an understatement of cosmic proportions. In a span of time so brief, it has no meaningful analogy in our daily lives. From perhaps a 10 trillionth of a trillionth of a trillionth of a second to a mere fraction of a second, the cosmos underwent a transformation so extreme it redefines the word growth. During inflation, the universe did not just get bigger, it increased in size by a factor of at least 10 to the power of 26. That is a 1 followed by 26 zeros. Let us try to frame that number in a way our minds can grasp, even if only for a moment. If the universe at the start of inflation was roughly the size of a single proton, smaller than an atom, by the end of that fleeting instant, it would have been larger than the entire observable universe we see today. Another way to picture it, if the pre-inflation cosmos was a simple marble, after inflation it would be larger than the real-life orbit of Pluto, not once, not 1,000 times, but millions of times over. This is the exponential power of doubling, where each successive step dwarfs all that came before. This leads to a natural and startling question. How could anything expand faster than light? The key is to remember that inflation was not matter racing through space. It was space itself, the very fabric of reality, stretching outward. There is no universal speed limit on the expansion of the stage itself. Objects embedded in that space were carried apart as the canvas grew, a process that does not violate the cosmic speed limit that applies only to motion through space. This phenomenal superluminal stretching is precisely what solves the great puzzles. It took a tiny, interconnected, smooth region and blew it up to encompass everything we can possibly observe, ironing out any wrinkles and creating the vast, flat theater we now inhabit. Every galaxy, every star, every planet you have ever seen in a telescope image originated from a quantum speck, magnified to cosmic proportions by this engine. Contemplating such numbers can feel abstract, almost disorienting. They push our intuition to its absolute limit, reminding us that the universe operates on a logic far grander than our everyday experience. Yet if this theory is true, if this unimaginable stretching truly occurred, it must have left a mark. Such a violent, foundational event would have imprinted a signature onto the cosmos, a whisper from the first moment that we might still be able to detect today. The horizon problem was not just a puzzle, it was a fundamental contradiction. Distant regions of the cosmos, forever isolated by the finite speed of light, displayed a perfect thermal harmony they should never have achieved. It was as if two orchestras on opposite sides of the world, who had never heard each other, began playing the same symphony in perfect unison. This demanded an explanation. The power of cosmic inflation lies in its elegant, almost breathtakingly simple resolution to this paradox. Before the inflationary burst, the entire seed of our observable universe was unimaginably small, a region so tiny that every part of it was in intimate causal contact. Heat could flow freely, particles could interact, and the temperature could smooth itself out into a perfect, uniform equilibrium. This was the initial condition, a warm, homogeneous speck. Then the inflationary engine ignited. In that fraction of a second, it did not merely expand this speck, it magnified it. The entire smooth, connected region was stretched to a scale far, far larger than the entire cosmos we can see today. Think of two neighboring grains of sand on a microscopic beach. Now imagine that entire beach is inflated to become the size of the Earth. Those two grains are now separated by thousands of miles, yet they share an identical origin, the same mineral composition, the same thermal history. This is what inflation accomplished. The distant galaxies we see on opposite sides of the sky today were once cozy neighbors, close enough to exchange energy and reach a common temperature before being carried apart by the stretching of space itself. The cosmic microwave background, that ancient afterglow from the early universe, is the ultimate proof of this process. Its temperature is uniform to better than 1 part in 100,000 across the entire sky. This incredible smoothness is not a mysterious coincidence. It is the direct, magnified imprint of that primordial, connected speck. Inflation takes the horizon problem and turns it inside out. The universe is not mysteriously uniform despite its size. It is uniform because its vastness came from an initial state that was small enough to become uniform. This was the theory's first major prediction, and it fit the observational data with stunning precision. Solving this deep cosmological riddle provided a powerful pillar of support, suggesting that this wild idea of exponential stretching might just be the key to our origin story. But a smooth universe is only the beginning of the tale. If inflation only created perfect smoothness, we would not be here to talk about it. We need structure, we need the seeds of galaxies, and remarkably, inflation had a mechanism for that too, born from the quantum chaos of the very vacuum it was stretching. Perfect smoothness solves one mystery, but it creates another. A universe without any variation, without any seeds of structure, would remain a featureless sea of hot gas forever. Stars would never ignite, galaxies would never form, and we would not exist to ponder its origins. The inflationary model needed a way to introduce the slightest imperfections, the quantum seeds for all future structure. And remarkably, the mechanism was built into the engine itself. The same quantum uncertainty that governs the subatomic world was at play during inflation. Even as space stretched exponentially, the energy field driving the expansion, the inflaton field, was subject to tiny, unavoidable quantum fluctuations. These are not fluctuations in matter, but in the very fabric of energy that powered the stretching. In some regions, the field had a slightly higher value, causing inflation to end a fraction of a moment later. In adjacent regions, a slightly lower value meant inflation ended a touch sooner. These minute differences in timing translated directly into minute differences in density. Regions that inflated a bit more ended up ever so slightly less dense, while regions that stopped inflating a fraction earlier were a tiny bit more dense. Inflation then took these quantum whispers, these microscopic ripples in the energy field, and stretched them to astronomical scales. What began as a quantum fuzz smaller than a proton was magnified into vast, gentle hills and valleys in the density of the early universe. These are the primordial density fluctuations, the cosmic blueprint for everything to come. After inflation ended and the universe filled with hot plasma, gravity went to work. It began to pull matter toward those slightly denser regions. Over billions of years, those subtle gravitational wells would draw in more and more gas, eventually collapsing into the first stars, the first galaxies, and the great cosmic web we observe today. Every galaxy cluster, every filament of dark matter, every void in space can trace its lineage back to those quantum ripples amplified during inflation's furious expansion. This is perhaps the most profound prediction of the theory, that the largest structures in the cosmos were seeded by the smallest possible fluctuations in the quantum vacuum. It directly links the dominion of the incredibly small to the architecture of the incredibly large, but a prediction is only as good as its evidence. Could we possibly find a fossil record of these primordial ripples, a snapshot of the universe when it was just a newborn? These quantum ripples were not just theoretical noise, they were the universe's first brushstrokes on a blank canvas. The Heisenberg uncertainty principle tells us that even a perfect vacuum is never truly still. It is a seething sea of virtual particles flickering in and out of existence. This quantum jitter applied to the inflatoned field itself, the energy driving the great expansion. At these unimaginably small scales and energies, the field experienced tiny, random variations in its value. In one region, it might be a fraction higher, in an adjacent region, a fraction lower. These differences were vanishingly small, but they were everywhere, an intrinsic fuzziness woven into the fabric of reality. Then inflation did something extraordinary. As space stretched faster than light, it did not smooth these fluctuations away. It locked them in and magnified them. A microscopic quantum bump, smaller than a proton, was stretched across light years, then across millions of light years. The process was like taking the fine grain of a piece of wood and stretching that grain to the size of a continent. What began as a quantum whisper became a permanent, gentle undulation in the density of the cosmos. When inflation finally ended and the universe filled with the hot soup of particles, these frozen ripples translated directly into the first real differences in the cosmos. Places where the inflatoned field had been slightly higher became regions of slightly lower density because they inflated a tiny bit more. Places where it was slightly lower became the seeds of higher density. The entire universe was imprinted with a pattern of incredibly subtle hills and valleys in the density of matter and energy. This pattern is the primordial blueprint, the cosmic fingerprint from which everything we see was built. Gravity is an amplifier of contrast. Over the next several 100 million years, it began to work on this blueprint. Every slight overdensity exerted a slightly stronger gravitational pull, drawing in nearby matter from the surrounding, slightly underdense regions. As more matter fell in, the gravitational pull grew stronger, attracting even more. The gentle hills in the density field became deep wells, the valleys became vast, empty spaces. From these gravitational seeds grew the first clumps of dark matter and gas, which collapsed to form the first stars, the first galaxies, and eventually the immense web-like structure of the modern universe. This means the spiral arms of the Milky Way, the vast emptiness of the Boötes void, and the great wall of galaxies stretching across the sky, all trace their ultimate origin back to those quantum fluctuations. The largest structures in existence are direct descendants of the smallest events possible. It is a connection of breathtaking elegance, linking the rules that govern subatomic particles to the architecture of the cosmos itself. But a blueprint is one thing. We needed to see it to believe it. Could we find a way to take a picture of this primordial fingerprint, to see the universe as it was before a single star was born? To find that primordial blueprint, we needed a time machine. Fortunately, the universe provided one in the form of the oldest light we can see. This is the cosmic microwave background, a faint, cold glow that fills every corner of the sky. It is the afterglow of the Big Bang itself, a snapshot of the universe frozen in time when it was a mere 380,000 years old. Before that moment, the cosmos was an opaque, searing plasma, a dense fog of particles and light. But as it expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, and the universe suddenly became transparent. That first burst of light released from the plasma has been traveling through space ever since, stretched by cosmic expansion into the microwave radiation we detect today. This ancient glow is our most direct window into the infant universe, a baby picture taken long before the first star was born. And according to the theory of inflation, this picture should bear very specific, telltale fingerprints. First, the temperature of this background radiation should be almost perfectly uniform, a direct consequence of that primordial speck being inflated to cosmic size. But crucially, it should not be perfectly smooth. Imprinted upon that uniform sea should be the faintest of patterns, tiny variations in temperature of just a few millionths of a degree. These anisotropies, as cosmologists call them, are the direct descendants of those quantum density ripples. Regions of slightly higher density from the inflationary era would appear as slightly cooler spots in the microwave background because the light climbing out of those deeper gravitational wells lost a tiny bit more energy. Slightly lower density regions would appear as warmer spots. Inflation made a bold, precise prediction about the statistical nature of these hot and cold spots. They should follow a specific pattern of distribution across different angular scales on the sky, a signature that would be extremely difficult to produce by any other known process. Even more specifically, inflation predicted that these temperature fluctuations should exhibit correlations over very large angles, a pattern that stems directly from the mechanism of superluminal stretching. For decades, these predictions were just theoretical speculation. Then we began to look. Satellite missions were launched with one primary goal: to map this ancient light with ever greater precision. The Cosmic Background Explorer, or COBE, made the first groundbreaking detection of these tiny anisotropies in the early 1990s, revealing the universe's primordial lumpiness. Its successors, the Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite, mapped the cosmic microwave background with breathtaking detail. The results were a triumph of observational cosmology. The patterns they found in the sky, the statistical distribution of hot and cold spots, matched the predictions of the inflationary model with stunning, almost uncanny accuracy. The specific correlations over large angles were there, just as the theory said they should be. This concordance between prediction and observation is not just a minor point of agreement. It is considered some of the strongest evidence we have that an epoch of exponential, inflationary expansion truly did occur in the first moments of time. The cosmic microwave background is more than an echo. It is a fossilized imprint of the universe's quantum origins, and its message powerfully supports the story of inflation. Yet, for all its success, this story is not complete. The cosmic microwave background gave us a map of the primordial density ripples, but inflation predicted another, even more elusive echo. Beyond those gentle hills and valleys in temperature, the theory said there should be ripples in the very fabric of spacetime itself, generated by the violent quantum fluctuations of gravity during that exponential stretch. These are primordial gravitational waves. If the temperature fluctuations are like sound waves echoing through the early universe, these gravitational waves would be the shuddering of the stage itself as it was being built. Their detection is considered one of the holy grails of modern cosmology for a profound reason. While the density ripples could, in principle, be generated by other mechanisms, a certain type of gravitational wave signature would be a unique, smoking gun for cosmic inflation. These waves would not be the kind detected by observatories like LIGO, which come from cataclysmic events like black hole mergers billions of years later. These would be fossils from the universe's first instant, stretched to wavelengths that could span the cosmos. They would carry a direct imprint of the unimaginable energy at which inflation occurred, offering a glimpse of physics at nearly the Planck scale, a realm 1 trillion times more energetic than anything our particle colliders can reach. So how do we hunt for such a faint whisper from the dawn of time? we look for its imprint on that same cosmic microwave background. When the ancient light from the Big Bang finally broke free, its journey was shaped by everything it passed through, including these spacetime ripples. Theorists realized that primordial gravitational waves would leave a specific, swirly pattern in the polarization of that light, a signature known as B-mode polarization. Finding this pattern is the ultimate goal. The search demands extreme conditions, places where the atmosphere is thin, dry, and stable. This is why teams have built sophisticated telescopes at the South Pole, high on the Chilean plateau, and even launched balloons into the stratosphere. Experiments with names like BICEP, Keck, and the Simons Observatories stare at patches of sky for years, collecting photons with exquisite sensitivity, trying to tease this faint swirl from the foreground noise of our own galaxy's dust and other cosmic signals. The pursuit has seen both excitement and sobering lessons. In 2014, one team announced a tentative detection of this B-mode signal, a moment that sent ripples of excitement through the scientific community. However, further analysis with data from the European Space Agency's Planck satellite revealed that the signal could be entirely explained by a more mundane source, interstellar dust within our own Milky Way. It was a powerful reminder of the immense challenge of this search, separating a whisper of creation from the cosmic static of our galactic neighborhood. Yet the quest is far from abandoned. It has been refined. The hunt continues with ever more sensitive instruments and better methods for subtracting that dusty foreground. Finding the primordial B-mode signal would be a discovery of Nobel Prize magnitude. It would not merely confirm that inflation happened, it would tell us about the specific physics of the inflationary engine, the energy scale at which it operated, and potentially even reveal the identity of the inflaton field itself. It would open a direct window to the universe at a time when all forces were one, a portal to the very frontier of known physics. This search represents a beautiful convergence of the largest questions and the most precise measurements, a testament to our enduring desire to understand where the grand stage of our existence came from and what trembled it into being. The evidence from the cosmic microwave background is compelling, but it does not point to a single, definitive script for that first moment. Instead, inflation is best understood as a vibrant, sprawling framework, a family of possible stories about how that exponential stretching unfolded. Think of it like a grand library of creation myths, each with its own subtle variations on the core plot. This collection of ideas is known as the inflationary landscape. The central character in most of these stories is a field, often called the inflaton field, whose energy powered the expansion, but the details change dramatically from model to model. In some versions, like chaotic inflation, the field starts from a random, high-energy point on its potential energy landscape and slowly rolls down a gentle slope, driving a long period of expansion. In others, like new inflation, the field becomes trapped in a false valley, a metastable state before quantum tunneling triggers its release. Hybrid models combine elements, using one field to drive the expansion and another to trigger its end. These are not just academic distinctions. The specific shape of that energy hill, the steepness of the slope, and the manner of the field's decay lead to different observable predictions. They forecast subtle variations in the statistical pattern of the hot and cold spots in the cosmic microwave background, and most crucially, they predict different strengths for the primordial gravitational wave signal we are searching for. A detection of those waves would not only confirm inflation, it would act as a cosmic tuning dial, helping us select the correct model from the many on the shelf. This diversity is both the framework's great strength and its most significant philosophical challenge. Its flexibility allows it to explain a wide range of possible initial conditions, but that very adaptability can make it feel, to some critics, almost too powerful to falsify. The quest now is to use ever more precise observations to navigate this landscape, to move from confirming the general idea of inflation to identifying the specific physical laws that governed it. This line of thinking naturally leads to an even more expansive question. If our universe is the product of one inflationary bubble, and the process relies on quantum fields settling into different energy states, could it have happened elsewhere under different conditions? Could there be a multitude of such bubbles, each giving rise to its own separate universe with potentially different fundamental constants and laws? The inflationary landscape might not just describe our past, but could hint at a reality far vaster and more strange than we ever imagined. The inflationary landscape is not a quiet, static place, but a seething, dynamic one. And if we follow the logic of its most potent equations to their ultimate conclusion, we arrive at a possibility so vast it redefines the word universe. This is the concept of eternal inflation. In this scenario, the process that birthed our cosmos never truly shuts down. Imagine our observable universe as a single bubble that formed when the inflattened field in our region decayed, releasing its energy to create our Big Bang. But what about the space beyond our bubble? According to this model, the inflationary background continues to expand at an exponential rate forever. And within that eternally stretching sea, quantum fluctuations can randomly kick the inflattened field back up to a high energy state in new, isolated patches. Each of those patches then undergoes its own burst of inflation, eventually decaying to form its own separate bubble universe, completely disconnected from our own. It becomes a self-replicating, endless process. One bubble gives rise to a region that spawns more bubbles in a chain reaction that has no end in time or space. This leads directly to the multiverse hypothesis. Our entire cosmos, with all its hundreds of billions of galaxies, becomes just one pocket in a boundless cosmic froth, a single soap bubble in an infinite, ever-growing foam. The profound implication is that each of these bubble universes could have experienced its own version of the field's decay, potentially resulting in different vacuum energies, different strengths for the fundamental forces, even different numbers of spatial dimensions. In this view, the fine-tuning of our constants, the fact that they allow for stars, planets, and life, is not a miraculous coincidence, it is a selection effect. We can only exist in a bubble where the constants are conducive to our form of complexity. Countless other bubbles with different laws may be sterile or transient, forever unobserved. While this idea emerges naturally from the mathematics of some inflationary models, it exists at the very frontier of science, bordering on philosophy. It is, by its nature, currently untestable, as these other universes would be causally severed from our own, hidden forever beyond our cosmological horizon. Yet it forces a profound shift in perspective. It asks us to consider that our entire reality might be a local event within a much grander, perhaps infinite, metastructure. The quest to understand our beginning may have led us to a vista where beginnings are commonplace, and the nature of reality itself is a tapestry of unimaginable variety. Such a grand vision rests on a foundation of elegant mathematics, yet not every physicist is convinced the story is complete. The very flexibility that makes inflation such a powerful explanatory framework has also drawn pointed criticism from some corners of the scientific community. A core concern is that, in its current form, inflation is what some call a paradigm rather than a single, falsifiable theory. With a vast landscape of possible models, each with adjustable parameters, critics argue it can be retrofitted to explain almost any pattern we might observe in the cosmic microwave background. This raises a philosophical question: how can a scientific idea be truly tested if it can always be adjusted to fit the data? Beyond this, the theory has its own internal puzzles. For inflation to begin in the first place, the universe must have already been in a very specific, smooth, and high-energy state. Explaining those initial conditions can feel like pushing the mystery one step further back in time. Then there is the graceful exit problem. The mechanism that starts inflation is one thing, but what triggers it to stop so precisely, converting that colossal vacuum energy into the hot plasma of the Big Bang without tearing the fabric of reality apart? In many models, this transition requires its own delicate fine-tuning. These are not trivial objections. They are serious challenges that keep theorists honest and drive the field forward. And inflation is not the only contender in the arena of cosmic origins. Alternative ideas exist, like the bouncing universe model, which proposes an endless cycle of contraction and expansion, or conformal cyclic cosmology, which envisions an infinite sequence of eons where the distant future of one universe becomes the Big Bang of the next. These frameworks attempt to explain the same smoothness and flatness we observe without invoking a period of exponential inflation. This competition of ideas is not a weakness of cosmology, it is its greatest strength. Healthy skepticism and rival theories are the engines of scientific progress, forcing each idea to sharpen its predictions and seek more definitive evidence. The true test lies not in philosophical debate, but in the cold, hard data yet to be collected. The quest for the universe's first whisper is far from over. It is now an engineering challenge of staggering ambition, pushing our technology to its absolute limits. The next chapter in this story will be written not just by theorists, but by teams of engineers building the most sensitive eyes ever turned toward the dawn of time. At the forefront are missions designed to capture the faintest possible signal from the cosmic microwave background, hunting for that swirling B-mode polarization pattern that could be the definitive signature of primordial gravitational waves. One such mission, proposed by an international collaboration, is LightBird, the light satellite for the study of B-mode polarization and inflation from dust. Its goal is singular and profound: to map the entire sky's microwave polarization with a sensitivity more than 10 times greater than any previous space mission. Operating from a stable point in deep space, far from Earth's interference, it would attempt to separate the inflationary whisper from the confounding noise of our galaxy's dust with unparalleled clarity. On the ground, the quest continues in the thin, dry air of high-altitude deserts and the frozen stillness of the Antarctic plateau. Observatories like the Simons Observatory in Chile and its planned successor, CMB Stage 4, are deploying arrays of tens of thousands of superconducting detectors. These instruments act like a cosmic microphone, listening to the faint hiss of the ancient light with such precision that they could detect temperature variations 1 billion times smaller than those we feel on a sunny day. Their detailed maps will scrutinize the statistical patterns in the CMB, testing the subtle predictions of different inflationary models against reality with razor-sharp accuracy. But the hunt extends beyond the afterglow of the Big Bang itself. Another revolutionary class of observatory is turning to a different kind of cosmic fossil, the neutral hydrogen gas that fills the vast voids between galaxies. Projects like the Square Kilometre Array, or SCAR, a network of radio telescopes spanning continents, will create a three-dimensional map of the universe's structure stretching back to its first billion years. By tracing the distribution of this primordial hydrogen, scientists hope to find an indirect imprint of those initial quantum ripples on a scale even larger than the CMB can show. This could reveal how inflation shaped not just the hot early plasma, but the very scaffolding upon which all later structure was hung. These are not separate endeavors, they are parts of a unified detective story. Each new observatory, whether in space or on remote mountaintops, provides a different lens, a different frequency, a different slice of cosmic history. Together, their data will form a cross-check of immense power. They will allow us to test the finer grains of the inflationary narrative, potentially ruling out entire families of models and guiding us toward the specific physics that ignited everything. The future of understanding our past is being built right now, in clean rooms and on barren plains, all in pursuit of an echo from a time when reality itself was being forged. The most powerful machine we have ever built, the Large Hadron Collider, smashes particles together at energies that can recreate conditions a trillionth of a second after the Big Bang. It is a monumental achievement, yet to peer into the era of cosmic inflation, we would need a collider with energies a trillion times greater, a machine larger than our solar system. This is an impossibility for any civilization. So how can we ever hope to understand the physics of that first fleeting moment? The answer is written across the sky. Inflation provides us with a natural cosmic laboratory, one that conducted the ultimate high-energy experiment at the beginning of time. The results of that experiment are encoded in the patterns of the cosmic microwave background and the large-scale structure of the universe. By decoding these patterns, we are indirectly probing physics at energy scales so extreme they approach the very limit of known theory, the Planck scale, where gravity becomes a quantum force. This makes cosmology our most powerful telescope, not just into deep space, but into the deepest laws of nature. At these incredible energies, the fundamental forces we know today are believed to merge into a single, unified superforce. This is the realm of grand unified theories, or GUT. In our cold, low-energy universe, we experience four separate forces: gravity, electromagnetism, the strong nuclear force that binds atomic nuclei, and the weak nuclear force behind radioactive decay. But in the searing heat of the universe's first moments, these distinctions would have blurred and then vanished. The electromagnetic and weak forces are already understood to unite into the electroweak force at high enough energies, a prediction spectacularly confirmed by particle colliders. Grand unified theories propose taking this further, merging the electroweak force with the strong nuclear force. The inflatoned field, the mysterious entity that drove the exponential expansion, may be a direct relic from this epoch of unification, a leftover vibration from when all forces except gravity were one. If this is true, then the specific signatures inflation imprinted on the cosmos, the precise statistical nature of the density ripples and the potential strength of gravitational waves are direct messages from the GUT era. They tell us about the symmetries and the particles that existed when the universe was a unified quantum field. This creates a breathtaking bridge between the largest and smallest scales of science. Particle physicists working with equations and collider data, and cosmologists mapping the ancient sky, are ultimately asking the same question: what are the fundamental rules of reality? The quest to understand inflation is therefore inseparable from the quest for a theory of everything. It pushes us inevitably toward the final frontier, quantum gravity. At the very instant inflation began, the universe was so small that quantum mechanical effects would have dominated the behavior of gravity itself. To truly understand the origin of space and time, we need a theory that successfully marries Einstein's theory of general relativity, which describes gravity as the curvature of spacetime, with the probabilistic, fuzzy rules of quantum mechanics. This is perhaps the greatest unsolved problem in theoretical physics. Current candidates like string theory or loop quantum gravity attempt to provide a framework. Inflation offers a potential observational test for these ideas. Certain features in the cosmic microwave background, or specific properties of the primordial gravitational wave spectrum, could carry the faint imprint of quantum gravitational effects from that first moment. In this way, the search for the origin of our cosmos becomes the most profound experiment imaginable in fundamental physics. We are using the entire universe as both the apparatus and the record, reading a story written in the language of quantum fields and spacetime geometry, a story that began when all of reality was a single, unified note. This quest leads us to the very edge of what our physics can describe. the inflationary epoch unfolded at such an unimaginably small scale and high energy that the universe itself was a quantum gravitational object. At that moment, the smooth curvature described by Einstein's general relativity would have been replaced by a seething, probabilistic foam, where the concepts of space and time as we know them break down entirely. To truly understand the ignition of inflation, we cannot rely on our classical picture of gravity. We need a theory that marries it with the quantum world. This is the monumental challenge of quantum gravity, the final piece in the puzzle of fundamental physics. It is the search for a single framework that can describe the force that shapes galaxies and the strange rules that govern particles. Leading candidates like string theory or loop quantum gravity offer different mathematical pathways to this unification, painting radically different pictures of reality's bedrock. String theory proposes that the fundamental entities are tiny, vibrating strings, with different vibrations corresponding to different particles and forces. Loop quantum gravity suggests that space itself is woven from a network of discrete, quantized loops. Both approaches and others attempt to provide a coherent description of the universe at the Planck scale, the realm where inflation began. This makes the early universe our only viable laboratory for testing these profound ideas. Some models within these frameworks propose that inflation did not emerge from a singular point, but from a prior state. One compelling idea is the quantum bounce, where our expanding universe is the rebound from a previous phase of contraction, with inflation naturally arising from the transition. In such a scenario, the Big Bang is not the absolute beginning, but a transformative event in an eternal cycle or a transition from a timeless quantum state. The detailed predictions of inflation, the specific statistical fingerprint it left on the cosmos, could therefore carry subtle imprints of these deeper quantum gravitational processes. By refining our observations of the cosmic microwave background and the large-scale structure of the universe, we are not just testing cosmology, we are conducting an indirect experiment on the nature of spacetime itself. A precise measurement of primordial gravitational waves, for instance, could reveal the energy scale of inflation, telling us if it occurred near the Planck energy where quantum gravity must take over. Certain patterns in the distribution of galaxies might hint at discrete properties of space woven into the fabric of the early universe. In this way, the quest to understand our cosmic origin has become inextricably linked to the greatest theoretical pursuit in physics. Each new map of the ancient sky, each incremental refinement in our data, is a message in a bottle from the quantum gravitational dawn, offering clues to a theory that would finally explain how space, time, and everything within them came to be. There is a profound beauty in a simple idea that explains so much. While the evidence from the cosmic microwave background provides a compelling case, part of inflation's enduring appeal lies in its breathtaking economy of thought. With a single, elegant mechanism, a fleeting epoch of exponential expansion, it untangles multiple, deep cosmological knots at once. The horizon problem of disconnected uniformity, the flatness problem of a knife-edge geometry, the puzzling absence of exotic magnetic monopoles, and the very origin of all cosmic structure, all find a natural resolution within this one framework. It is a masterstroke of explanatory power, turning a collection of baffling coincidences into the predicted outcomes of a single, coherent process. This kind of unifying narrative is the gold standard in science. It transforms our origin story from a mysterious, singular event into a dynamic, physics-driven narrative, a story with a beginning, a middle, and a set of consequences we can still observe today. This aesthetic elegance, the sense that the pieces fit together with such satisfying logic, is a powerful guide. It suggests we are on the right track, that we are glimpsing a deeper order beneath the apparent chaos of the cosmos. Yet, history is littered with beautiful theories that were ultimately wrong. Elegance alone is not proof. it must be relentlessly tested against the cold, hard data of reality. The true strength of inflation is that it marries this conceptual beauty with a wealth of specific, testable predictions. Its appeal is not just in its simplicity, but in its ability to invite scrutiny, to tell us exactly what fingerprints its engine should have left behind for us to find. This balance between the guiding light of elegant explanation and the grounding force of empirical evidence is the very engine of scientific progress. It reminds us that while a beautiful theory can illuminate the path forward, we must always let the universe itself have the final word. The elegant equations of inflation do more than describe our past, they open a door to a reality of staggering scale. If the process of eternal inflation is correct, then our cosmos, with all its hundreds of billions of galaxies, is not the universe. It is merely a universe, one bubble in an endless, frothing sea of cosmic foam. This is the inflationary multiverse, and it carries philosophical weight that reshapes our understanding of existence itself. For centuries, the Copernican principle taught us a humbling lesson. We are not at the center of the solar system, nor the galaxy, nor the cosmos. The multiverse idea extends this humility to a breathtaking extreme. Not only are we not at the center of anything, but the entire stage we perform on may be utterly ordinary, one of countless similar stages in an infinite meta-theater. Our laws of physics, the constants that seem so finely tuned to allow for stars, planets, and life, may not be fundamental truths written into the fabric of reality. They could be local bylaws, the accidental outcome of how the inflattened field decayed in our particular bubble. In other bubbles with different decays, the strength of gravity might be stronger, the nuclear forces weaker, or the number of spatial dimensions different. Some of those universes might be stillborn, collapsing instantly or expanding into barren emptiness. Others might be wildly exotic, governed by physics we can scarcely imagine. This leads directly to the anthropic principle, a controversial but fascinating line of reasoning. It suggests that the constants we observe are not randomly fine-tuned for us, but rather, we can only observe constants that allow for observers like us to exist. In an infinite multiverse where every possible set of laws is realized somewhere, it is no surprise that we find ourselves in one of the rare, hospitable pockets. This is not an explanation for why our constants have their values, but it changes the nature of the question entirely. The inquiry shifts from why are the laws this way, to what must the laws be like in a universe that contains beings who can ask such questions. These ideas blur the boundary between science and philosophy, between empirical discovery and metaphysical speculation. They force us to confront the very meaning of existence. If all possible universes are realized in the multiverse, does that make our choices, our history, our unique narrative less meaningful, or in a strange way, more universal? We are left gazing at the night sky with a renewed sense of scale, pondering not just distant stars, but distant realities, each with its own story, its own laws, its own potential for wonder. Conveying the scale of cosmic inflation is a challenge for the human mind. Our intuition is built on a world where objects move through space, not where space itself is the thing stretching at an impossible rate. To bridge this gap, we rely on analogies, turning the unseeable into visual stories we can grasp. The most familiar is the inflating balloon. Picture dots drawn on the surface of a balloon. As you blow it up, every dot moves away from every other dot. No single dot is at the center of the expansion. The center is inside the balloon, a dimension not part of the surface. This beautifully illustrates how galaxies recede from each other as space expands. But it has a limit. It suggests the universe is expanding into something, like the balloon expands into a room which isn't quite right. A more accurate, if less elegant, image is raisin bread dough. As the dough bakes and expands, each raisin moves farther away from all the others. The raisins themselves aren't growing, they're being carried apart by the stretching dough, which represents space itself. This gets closer to the heart of the matter, but to visualize the radical nature of inflation itself, we need to go further. Imagine a checkerboard pattern printed on a perfectly elastic rubber sheet. During the universe's normal, steady expansion, that sheet stretches slowly. The squares of the checkerboard simply get larger over time. Now picture the inflationary epoch. The rubber sheet isn't just stretching, it is being pulled with such ferocious speed that entirely new squares of the checkerboard are being generated in the gaps between the old ones. Space isn't merely getting bigger, it is being created, proliferating at a rate that defies common sense. This is the exponential magic of inflation, where the fabric of reality multiplies itself. These thought experiments are more than just teaching tools, they are essential bridges. They allow us to take a concept that operates at scales of a trillionth of a second and translate it into a form our pattern-seeking brains can work with. Coupled with sophisticated computer simulations that model the quantum ripples and their stretching into galactic superclusters, these analogies make the epic narrative of our origin accessible. They transform abstract equations into a story we can see in our mind's eye, fostering a sense of awe not just for scientists, but for anyone who looks up at the night sky and wonders how such immensity came to be. Our cosmic origin story has been rewritten more than once. For most of human history, the dominant view was of a static, eternal cosmos. The stars were fixed points on a celestial sphere, and the universe was considered unchanging and essentially infinite in both space and time. This was a comforting, stable backdrop against which human drama unfolded. That certainty shattered in the early 20th century. Edwin Hubble's observations of receding galaxies revealed a universe that was not static, but expanding. Space itself was stretching, carrying galaxies apart like dots on an inflating balloon. This led directly to the Big Bang theory, the revolutionary idea that the universe had a fiery, dense beginning a finite time ago. It was a monumental paradigm shift, moving us from an eternal cosmos to one with a dramatic origin story. Yet, as we explored, that story revealed its own puzzling gaps. The classic Big Bang model could not explain the universe's profound smoothness or its precise geometric flatness. The theory was powerful but incomplete. Into this gap stepped cosmic inflation, a refinement born not from discarding the Big Bang but from deepening it. Inflation proposed a breathtaking prologue, a fleeting instant of exponential expansion that set the perfect initial conditions for the hot Big Bang to unfold. This progression from a static stage to an expanding one to one that inflates is a perfect illustration of how science truly works. It is not a collection of unchanging facts, but a self-correcting, evolving narrative. Each new chapter does not erase the old one, it builds upon it, incorporating new data and sharper theoretical insights to paint a more complete and coherent picture. The static universe gave way to the expanding one when the telescope's eye saw galaxies fleeing. The expanding universe welcomed the inflationary prologue when its mathematical elegance solved deep observational puzzles. This history reminds us that our current understanding, including inflation, is almost certainly not the final word. It is the best chapter we have written so far, based on the evidence before us. The story is ongoing, and the next chapter is being drafted right now, not just in the minds of theorists, but in the vast streams of digital data flowing from our telescopes, creating a living, ever-improving map of our cosmic past. The grand narrative of cosmic inflation is not confined to textbooks and telescopes. Its echoes have subtly permeated the broader cultural landscape, offering a new kind of creation myth for our time. Unlike the immediate visual drama of a black hole or the tantalizing promise of a wormhole, inflation's story is one of abstract, invisible forces acting on the fabric of reality itself. This makes it a more challenging concept to dramatize, yet its implications are so profound that they have become fertile ground for science fiction. In many modern comics, novels, and films, when a character speaks of parallel realities or a branching multiverse, the underlying mechanics often draw inspiration from inflationary cosmology. The idea of eternal inflation, with its endless bubbling of new universes, provides a scientifically plausible scaffolding for fictional worlds where every choice spawns a new timeline, or where heroes can travel between radically different realities. This cultural seepage is significant. It transforms a complex theoretical framework into a shared imaginative space, allowing the public to grapple with concepts of cosmic scale and quantum origin through the powerful lens of story. This translation from academia to popular understanding has been powerfully aided by landmark documentary series. Programs like the rebooted Cosmos have brought the stunning visual metaphor of the inflating universe into living rooms around the world. Through state-of-the-art animation, viewers have watched as a subatomic speck undergoes that exponential, reality-stretching transformation, blossoming into the cosmic web we recognize. These portrayals do more than educate, they inspire awe. For a young person watching, that moment of revelation can be transformative, planting the seed of curiosity that grows into a career in physics or astronomy. This public engagement is vital, as it builds broad support for the fundamental, curiosity-driven research that pushes these boundaries without immediate practical application. It reminds society that asking the deepest questions about our origin is a worthy human endeavor, yet with popularization comes a necessary caution. The line between established science and speculative extension can blur in cultural retellings. The core idea of an early epoch of exponential expansion, supported by detailed evidence from the cosmic microwave background, is robust. The extension of that idea into an infinite, disconnected multiverse of alternate realities is a profound and compelling possibility that emerges from the math, but it remains firmly in the realm of theoretical speculation. As we enjoy narratives built upon these ideas, it serves us to maintain that distinction, to appreciate the solid ground of discovery while marveling at the majestic horizons of possibility it reveals. This discernment allows us to celebrate the cultural impact of inflation while honoring the rigorous, evidence-based journey of science itself. The drive to listen for the universe's first whisper does more than satisfy our deepest curiosity. It pushes human technology to its absolute limits. To detect the faint polarization patterns in the cosmic microwave background, scientists must build instruments of almost unimaginable sensitivity. This requires breakthroughs in the coldest realms of physics, operating detectors at a fraction of a degree above absolute zero. The pursuit has accelerated the development of advanced superconductors, ultra-precise cryogenic systems, and exquisitely sensitive bolometers that can measure the energy of a single photon. These are not just laboratory curiosities. The technologies forged in the quest to map the infant universe often find second lives here on Earth. The same superconducting sensors designed for telescopes at the South Pole can be adapted for more sensitive magnetic resonance imaging, or MRI, machines, potentially leading to earlier and more detailed medical diagnoses. The advanced cryogenics developed to keep space telescopes cold are refining our ability to store and transport vital materials, from biological samples to clean energy fuels. Even the complex algorithms created to filter cosmic signals from foreground noise contribute to the broader field of big data science, enhancing everything from weather forecasting to financial modeling. This is a recurring theme in the history of fundamental research. The tools we build to answer the biggest questions inevitably sharpen our ability to solve the most human ones. Furthermore, these monumental projects are exercises in global cooperation. A single cosmic microwave background observatory often involves hundreds of scientists, engineers, and technicians from dozens of countries, all working toward a common goal that transcends borders. This collaborative framework trains a generation of problem solvers, equipping them with skills in advanced computing, systems engineering, and data analysis that are in high demand across the technology sector. The student who writes code to clean cosmic data today might develop the next breakthrough in machine learning tomorrow. So while we gaze outward to understand our origin, we are simultaneously building a more capable, connected, and innovative world right here. The value of asking where we came from is measured not only in cosmic insight, but in the tangible progress it sparks for all of humanity. A theory this profound inevitably gets simplified, and with simplification come common misunderstandings. One of the most frequent points of confusion is the relationship between inflation and the Big Bang. Cosmic inflation is not the Big Bang itself, it is the breathtaking prologue. The Big Bang, as we traditionally describe it, is the hot, dense, expanding state that began when inflation ended. Think of it like the opening act of a grand play. Inflation built the vast, smooth, and flat stage. The moment that stage was flooded with light and particles, that was the curtain rising on the hot Big Bang narrative we have long studied. Another persistent misconception involves speed. Many hear that the universe expanded faster than light and picture galaxies racing through space like cosmic speedsters. This is not what happened. The objects themselves were not moving through space. Space itself, the very fabric of reality, was stretching. There is no universal speed limit on the expansion of the stage, only on motion across it. This distinction is crucial. It resolves the paradox and is the very reason inflation solves the horizon problem. A more subtle but equally important point concerns energy. At first glance, the idea of space creating more space and filling it with matter seems to violate a sacred law, the conservation of energy. Where did all this new energy come from? The answer lies in a beautiful cosmic balance sheet made possible by gravity. The positive energy locked in the mass of every star, planet, and particle is precisely balanced by a vast reservoir of negative gravitational potential energy created by the expansion itself. As the universe stretches, this gravitational debt grows deeper, perfectly offsetting the apparent gain. In the grand total of the cosmos, the net energy may very well be zero. A profound thought suggesting everything we see could be a magnificent fluctuation on a ledger that ultimately sums to nothing. Finally, it is essential to understand what inflation does and does not explain. The theory provides the origin of the seeds, the subtle blueprint of density ripples imprinted on the cosmos. But it does not build the cosmic cities. The actual formation of galaxies, stars, and planets was the work of gravity, acting over billions of years on those initial seeds. Inflation set the initial conditions with exquisite precision, but it was the patient, relentless pull of gravity that sculpted those quantum whispers into the grand galactic structures we observe today. Clarifying these points is not just academic, it allows us to appreciate the true scope of this idea. A specific and powerful mechanism that answers foundational questions about our universe's setup, while leaving the later, equally epic story of cosmic construction for the forces that followed. These vast cosmic maps from our telescopes are not the final step, they are the raw data for the ultimate experiment, to test whether a specific version of that inflationary whisper truly leads to our universe. We need to run time itself forward. Since we cannot replay creation, we build a digital universe inside the world's most powerful supercomputers. This is computational cosmology, a field where the birth of galaxies is simulated with billions of particles of virtual dark matter and gas. Scientists begin with a simple seed, a mathematical representation of the precise pattern of quantum ripples predicted by a particular inflationary model. They then program in the known laws of physics, gravity, hydrodynamics, and the behavior of dark energy, and set the simulation running. Over months of real time, the computer calculates the gravitational dance of trillions of particles across billions of virtual years, watching as those initial ripples collapse into dark matter halos, which then pull in streams of gas to ignite the first stars and forge swirling galaxies. The result is not a simple animation. It is a rich, three-dimensional synthetic cosmos, complete with its own virtual sky surveys. Researchers can then fly through this digital universe, measuring the distances between simulated galaxies, the shapes of clusters, and the distribution of cosmic voids. They compare these statistics directly to the measurements from real projects like the Sloan Digital Sky Survey. Does the simulated universe, born from a specific inflationary blueprint, grow to look statistically identical to our own? If the patterns match, that inflationary model gains powerful support. If they diverge, the model may need revision or be ruled out entirely. This process turns the history of the cosmos into a repeatable laboratory experiment. We are no longer passive observers of a single, finished universe. We are active testers of its origin story, running countless variations in silicon to find the one set of initial conditions that leads inevitably to the majestic cosmic web we call home. The story of our cosmos is written into our very atoms. Every element heavier than hydrogen and helium, the carbon in our cells, the oxygen we breathe, the iron in our blood, was forged in the fiery hearts of ancient stars and scattered across space by their explosive deaths. Those stars themselves could only ignite because of the gentle gravitational wells seeded by quantum ripples during inflation. This means the calcium in your bones and the silicon in the earth beneath your feet are direct descendants of a microscopic fluctuation in the first sliver of time, stretched across the entire observable universe. We are not just living in this cosmic story, we are a physical manifestation of it, stardust that has become conscious and begun to trace its own lineage back to the beginning. This realization carries a unique and humbling weight. The scale involved is so immense it can feel disorienting. Our entire galaxy, with its hundreds of billions of stars, is but one faint spark in a cosmic web that itself is just one bubble in a potentially infinite foam. Our planet is a pale blue dot orbiting an unremarkable star in a quiet suburb of that galaxy. And yet, from this tiny vantage point, we have pieced together the epic narrative of cosmic inflation, of quantum whispers and exponential stretching. We have built instruments to capture the faint afterglow of creation and devised mathematics to describe its first unimaginable moments. There is a profound duality in this perspective. It reveals our apparent insignificance within the vast arena of space and time, while simultaneously highlighting the extraordinary significance of our capacity to understand it. This cosmic context does not diminish our lives, it enriches them with a deeper sense of connection. The same physical laws that govern the spin of galaxies and the decay of a false vacuum also govern the chemistry of life and the firing of neurons that allow us to ponder these very ideas. This viewpoint, grounded in evidence and discovery, offers a form of meaning rooted in relationship and continuity. It tells us we are intimately woven into the fabric of the cosmos, not as passive spectators, but as active participants in an ongoing story of transformation that began nearly 14 billion years ago. It invites a quiet awe, a recognition that to look up at the night sky is to look back at our own deepest origin, and to wonder what other chapters in this grand narrative are yet to be understood. The search for that first cosmic whisper cannot be confined to a single discipline. It sits at a spectacular crossroads where the sharpest tools from vastly different fields of human knowledge converge. To truly grasp cosmic inflation, you need the language of particle physics to describe the inflaton field, that mysterious entity whose energy powered the stretch. You need the sweeping geometry of Einstein's general relativity to model how spacetime itself can expand exponentially. You then turn to the probabilistic rules of quantum mechanics to understand the origin of the initial fluctuations, and the laws of thermodynamics to explain how that frozen vacuum energy transformed into a searing hot plasma. This is not a linear path, it is a constant dynamic conversation between domains. A breakthrough in understanding the symmetries of particle physics can reshape the predictions for what we should see in the ancient sky. A new, precise measurement of the cosmic microwave background can, in turn, rule out entire families of particle physics models. The dialogue is essential, each field providing a piece of the puzzle the others cannot see. But the convergence extends even further. To test these grand ideas, we rely on advanced computer science to run the immense simulations that grow virtual universes from quantum seeds. We depend on cutting-edge engineering and materials science to build the exquisitely sensitive detectors that sit in the cold darkness of Antarctica or orbit in the silence of space. And inevitably, the questions inflation raises about ultimate beginnings, fine-tuning, and the possibility of a multiverse spill over into the realm of philosophy, challenging our very conceptions of existence and reality. This vibrant interdisciplinarity is not a side effect, it is the core strength of modern cosmology. It creates an environment where breakthroughs often spark at the intersections, where a physicist's equation is solved by a mathematician's insight, and an engineer's new sensor makes a theorist's prediction testable for the first time. It exemplifies a profound truth about our quest to understand the cosmos. Solving the deepest mysteries requires synthesizing knowledge from every corner of human curiosity. This collaborative spirit, this willingness to bridge between languages and tools, is what allows us to stare back toward the dawn and slowly, piece by interconnected piece, decipher the story written there. The inflationary engine solved so many puzzles, but it did not answer the deepest one. It tells us with stunning clarity what happened in that first sliver of a second, yet it leaves us staring into an even greater abyss. What, or perhaps when, was the prime mover? What set the inflationary engine itself into motion? This is the ultimate question that lies at the precipice of our knowledge. We have traced the story back to a quantum seed, but we cannot yet say what soil that seed was planted in. Some theoretical pathways suggest inflation emerged from a prior state of existence, perhaps from a random quantum fluctuation in a timeless, pre-existing spacetime. In this view, our universe is a spontaneous bubble of order arising from an eternal, chaotic quantum foam. Other ideas, drawn from the depths of string theory, propose our cosmos was born from a cosmic collision. Imagine our three-dimensional universe as a membrane or brain floating in a higher dimensional space. The violent interaction between two such brains could have released the colossal energy needed to ignite inflation, like a stone striking a pond and sending out ripples that become an entire universe. There is also the compelling notion of a cyclic cosmos, one without a true beginning or end. In this eternal return, the universe undergoes endless cycles of expansion, contraction, and rebirth. The hot, dense state we call the Big Bang was not the absolute start, but simply the turnaround point from a prior phase of collapse, with inflation naturally emerging from the bounce. Each of these ideas pushes the origin story one step further back, but they all eventually confront the same formidable wall. Our current laws of physics, the very tools we use to describe reality, are built to operate within a framework of space and time. When we ask what happened before inflation, or what exists outside our bubble, we are asking about conditions where the concepts of before and outside may have no meaning. We are probing a realm where space-time itself may have emerged, a domain where causality as we understand it breaks down entirely. This is not a failure of science, but a recognition of its boundaries. It marks a frontier where empirical evidence meets profound philosophical inquiry. the question of what caused inflation may forever remain beyond the reach of direct observation, locked behind the veil of that first unimaginable moment. Yet, the very act of asking it, of following the chain of causality to its absolute limit, reshapes our understanding of existence. It forces us to consider that time may not be fundamental, that our universe may be a local event within a much grander and stranger meta-reality. This open frontier is not an ending but an invitation to a deeper, more humbling kind of wonder. From a single quantum whisper, an entire cosmic history unfolds. We have traced a story that begins not with a bang, but with a stretch, a fleeting moment of exponential expansion that set the stage for everything to come. Cosmic inflation provides a breathtaking narrative, solving the deep puzzles of our universe's smoothness and geometry, and planting the quantum seeds from which all galaxies would eventually grow. It stands as our most compelling framework, a bridge between the probabilistic flicker of the quantum world and the majestic architecture of the cosmos. This journey reminds us that our universe is not static, but a dynamic, evolving entity born from a process of profound and explosive change. The search for its final confirmation continues in the meticulous mapping of the ancient microwave sky and in the theoretical quests for quantum gravity. Each new observation, each refined measurement, brings us closer to understanding that first, unimaginable instant. The story of our origin is still being written, and we are here to read it. If exploring these fundamental mysteries of space and time captivated you, consider subscribing for more journeys to the edge of our understanding. We would love to hear your perspective on inflation and the ideas it inspires in the comments below.